interaction. So I'm here today to talk about under-the-table interaction. This was a piece of work done at Mitsubishi Electric Research Labs in collaboration with the University of Toronto. I'm presenting the work today, and it was also work done by Darren Lay, Clifton Forlines, who'll be giving a talk in a few minutes, Sam Shipman, John Barnwell, Professor Balakrishnan, and Cha Shen. Let's talk about under-the-table interaction. So the basic idea with under-the-table interaction is that we've taken a traditional tabletop surface and added an additional surface underneath the table, which will accept touch input. Now, in this image, we see my hand interacting on the top of the table and a rotoscoped image of my other hand working underneath the table. Throughout this talk and in the paper, we use this convention of diagrammatically depicting the hands so that you can see them. The prototype that we built was opaque, and we were therefore required to develop visualizations that would allow people to understand where their hands were. But just so you understand that when I'm going through the slides and you're able to see the hands that are underneath, it's just because we've chosen to depict it that way. So here is a user, Cha, working with our two-sided touch table. And the way that it was built was we took the diamond touch table, with which many of you are already familiar, and we added a second surface underneath it, taking great care to minimize the thickness so that the hands touching underneath are very close to the displayed surface on top. You can see, those of you who are familiar with the Diamond Touch know that it can accept multi-user input and is able to distinguish between the multiple users. So we see Cha interacting and her interactions are blue, and we see Cliff interacting and his interactions are shown in red. Now, the question that immediately comes up, of course, is why go under the table? Well, there are two motivations for this work. The first is that we wanted to try to address some of the issues with interaction that come up with traditional tabletops by adding this new surface underneath and leveraging its affordances. The next idea is that we wanted to look at new affordances that this platform would provide and to develop new interactions that make use of it. There are a couple of pieces of work that are directly relevant. There are many input devices where the hand reaches around on the front of the device. These two are of particular interest. They both come from Japan. The first is the behind touch, which I'm sad to say we discovered after the camera-ready version of the paper was submitted. We weren't able to get the Japanese translation in time. This piece of work uses a touch surface or a touch keypad behind the screen of a cell phone to make it easier for the blind to make text input. The hybrid touch technique is even more relevant. It is a PDA with traditional stylus input on the front. On the back of the PDA is a touchpad, and they use that touchpad to scroll the environment while they're able to simultaneously make input on the front, so that they can do things like draw on very large images that are larger than the size of the display by scrolling the landscape with their hand behind the screen. So let's talk now about how we've applied this idea to touch tables. And there are two distinct platforms where we can do under-the-table input. The first is an inverted table, where we take a traditional tabletop and just turn it upside down with the display surface still on the top, and all of the input is made underneath. The other, which is the one that we actually built, is the two-sided table, where you're able to make input to both the top and bottom. The distinction between these things is important for a couple of reasons. The first is that the inverted table would be less expensive to build. You could just take a tabletop that already exists, turn it upside down, and as long as the display would stay on top, you'd have an inverted touch table. The other reason that this is interesting is that an inverted table has affordances for use that a two-sided table doesn't necessarily afford. Although, of course, all of the things I'm going to talk about now about inverted tables would also apply to a two-sided touch table, because you could just turn off the input on the top of the table. So what I'm going to do now is go through a few of the affordances and interaction paradigms and some of the designs for each of these two platforms. I'll talk about the inverted table first and why we think this is an interesting platform for further development. First, we maintain that despite the fact the user is unable to see their hands while they're making input underneath the table, the direct touch input paradigm is maintained so that the user has some understanding that the touches they make underneath the table can be or should be directly applied to the screen that is directly above the hands. Now, we put an asterisk on that because what we found also was that we're able to break this paradigm when it doesn't suit us. And that although a piece of work that I'll talk about next told us that users don't like making input onto a screen if it's not in a direct touch manner, because their hand is occluded by the table in our case, we can dispose of the direct touch input paradigm when it's not convenient. So that's a nice property of this. Next, let's talk about targeting accuracy. A lot of people have the immediate reaction to say that once you can't see your hand anymore, it's much more difficult to make selections or to touch in an accurate way. What's interesting, though, is that if we leverage the techniques of a previous piece of work, we can actually make touch input on the bottom side of the table more accurate than input on the top. And the reason that's possible is if we look on the very left with a regular touch table, if this user were to move their hand to select one of these targets, once they do that, the target becomes occluded, and they're not able to make pixel-accurate selections, although designers of tabletops very often are working in an environment where they allow for pixel-level selections, despite the fact that with the direct touch input paradigm, we're not able to see that pixel. Potter, Schneiderman et al. Developed a solution to this problem by using what they call a lift-off technique, where they touch on the table and the crosshair is displayed about 1.5 inches above their finger, and selections are actually made by lifting their finger off the table. We are able to do that without breaking the direct touch input paradigm, because we can display the crosshair directly where the touch is happening, and it's still visible to the user. Potter et al. Make a note in their paper that users took great exception, that was the term that they used, to the idea of not having it be direct input when the input and display space are overlaid. Although there was an excellent piece of work presented earlier in the conference by colleagues of mine at Toronto and Merle that show another way that you can break that in an interesting way. So let me show you what this might look like. Cha is going to try to make a selection of a small target with a traditional tabletop. She's not able to target it accurately because as soon as she does, her finger occludes the target. So she goes underneath the table and makes the selection accurately with the crosshair. Another thing of interest to people making designs in this space, although of course we do support bimanual input on our table, the posture for bimanual input is different because the thumbs are now opposing one another instead of being towards one another. And that's something that, although we don't look at a lot in our design, it's something to think about when you're building bimanual interactions for an inverted table. Another property is that accidental touches are less likely. So what you'll see in this video is that two people are having a conversation on the tabletop, and one is being careful not to touch it. The other is just trying to converse, and he accidentally gives input to the table, to the great frustration of his colleague. Here, we're able to turn off the top so they can both make conversational gestures and actually touch the table. And when they agree on the input, Cha is able to make the selection underneath. Another issue to be considered is arm fatigue. This is something else that comes up a lot when I describe this work to people. In the user study that I'm going to describe in a few minutes, what we found was, although I won't be reporting this result directly then, the users actually preferred to make touches under the table in terms of fatigue. And the reason for that is, because the diamond touch is able to accept input from any part of the body, including the forearms, when users are making selections far away on the table, they can't rest their arm while they're making the selection. On our table, though, we built it a few inches above another table. It's not a touch table, it's just a regular piece of furniture. But because of that, the user is able to rest their arms while they're making selections and doing interactions underneath the table. There's actually less fatigue in this case. But people wishing to design something should consider doing that same thing in their hardware. A few more issues. The first is reduced reach. It is absolutely the case that a user is not able to reach as far when they're reaching underneath the table because the table is blocking their arm from making that touch. What previous results in tabletops have suggested, though, is that most of the primary work on a tabletop is done immediately in front of the user. So that's perhaps less of an issue than it might otherwise be. We also have reduced occlusion. So I mentioned the problem with making accurate selections is that you occlude the target. Another problem with direct touch input is that even in addition to the target, when you're making a selection, you occlude the rest of the display as well, and that won't happen if you're making touches underneath. The last property of an inverted table is that we're able to do private input. A number of pieces of work have emerged from this community that allow for private display of information on a public display using various technologies like shutter glasses. But all of those techniques have some amount of public input if the input device is shared by multiple users. In this case, though, the table actually hides the hand. So as long as the feedback to the user is private, then so too will the input be private. So those are all the properties of the inverted table. Now let's take a look at things that emerge from this platform when we enable the top surface of the table for touch input. First of all, it's important when people are designing for this type of platform to realize that the location of the hands, not just on the particular area of the surface, but also which surface they're touching on, should have an impact on semantics of interaction. So as you see in the top left, this user is making unimanual input to the bottom of the table. In the top right, they're making unimanual input to the top of the table. It is absolutely the case that you should not have the same interactions be on both the top and bottom. So these two actions should result in different things in your application. And we'll see a few examples of what those things might be. That's also true of when both hands are working underneath, as in the bottom left, or when the hands are split between two surfaces, as in the bottom right, or both hands on top of the table. So let's take a look at a few more of the affordances and properties of a two-sided table. First, one thing to consider with the hand location semantics is to couple the modes to the input on one side of the surface or the other. So in this application, we see the user is positioning a lens on top of a map that's showing satellite imagery with their top hand, and they're able to zoom and to pan underneath the table with their other hand. And this allows those operations to be done in a direct touch way without occluding the imagery that they're attempting to look at. Another property is that we're able to have colocality of bimanual input. So with a direct touch input device, two hands cannot touch in the same place at the same time, as this user is attempting to do, force her hands through each other. But once we move to two sides of the table, the user is able to put both of her hands in the same place at the same time. And this can enable interactions that might not otherwise be possible. We also have colocality of multi-user input. So two users can have input to the same place at the same time on the tabletop. We were accused by our reviewers of overacting in the video. I hope you'll agree that that was an unfair comment. We also have two new types of bimanual symmetry with a two-sided table. One is having the hands flailing back and forth in the same direction. I'll do it now. I have to pull the microphone away from my face. And also rotational symmetry, so that the two hands can be in opposition. We call it the pickle jar symmetry, so that they can rotate in opposition to each other. Both of these types of bimanual symmetry are not possible on a regular direct touch input device. Although we don't leverage them in any of the applications we describe in the paper, it's something to think about now that you're all going to be very excited and run out and build a two-sided table yourselves. Another property is that we reduce physical interference. So even if the user is not wishing to make input to the same place exactly on the table, even if the locations are not the same, the hands will bump into each other if they're trying to maintain contact with the touch surface. So in this case, we built a new version of the game Pong, where the user has two paddles and they attempt to trap the ball between them to accelerate it and fire it back at the other side with greater velocity. If the interaction you desire is that your hands stay on top of the paddles and the paddles move with your hands, if the input was being done on top of the table, the arms would bump into each other. But here we can see that by having one hand on top and one hand underneath, the user is able to very quickly defeat his opponent. And yes, it is underneath. Okay. Another property is the affordance of a 3D space. So this application I'm about to show is Takeo Igarashi's Teddy program. And what the user is going to be doing is working behind to do manipulations of the model. This is also an example of doing modal coupling. And the user is going to be moving and rotating the model from behind while doing drawing on the front. And we say that this affords a 3D space because unlike a regular tabletop, which you can think of as a camera into a space, perhaps, as in a desktop, here we have a front surface and a back surface. And you think of the 3D space as being squished in between those two surfaces. You're able to reach behind and do interactions on it. One interesting property of that is you see the user at the end there making rotations of the teddy bear. The user in this case is using, it's not quite arcball, but it's something very similar to arcball, in which the metaphor is we're grabbing some spherical object and it follows our hand while we're doing rotations. Once the hand moves underneath the table, in order to maintain the idea of a 3D space, you need to invert the arcball interactions to maintain this metaphor of I'm grabbing onto the object and it's following my hand, but in this case, we're grabbing it from behind. So that was an interesting idea, and people who use our system are able to use it inverted or not inverted, so that's an advantage of a two-sided table. Here's an idea of having alternative input mapping, and this leverages the notion I had before of the asterisk on the direct touch input. So here on top, the user is able to do direct touch input as with a normal touch table, with the right hand, but with the left hand, the user is sending input off to another space. So this is a way that we're allowing the user to break that direct touch input paradigm in an interesting way. So those are all of the properties that we describe in our paper of inverted and two-sided tables. Now, I want to take a minute to talk about the accuracy of under-the-table pointing. This is not a user study that validates our techniques, but rather we're interested to know whether or not we're telling the truth when we say a direct touch input paradigm is maintained with a two-sided table. So I already showed you that selection can be more accurate if you're touching underneath the table, but that's with liftoff selection with some visualization of the location of the hand. What we were curious about was how accurately does the user land on a target if they have no feedback about their hand location. Now, of course, you would probably not want to design a selection technique on this kind of platform that was done that way. But what this will tell us is how well the user understands where their hands are when they're working underneath the table and they're not able to see it. So we grabbed 8 participants from the community. We had them do target selection tasks on both sides of the table with the ordering switched between participants. There were 3 different target sizes. They were circles that were 1 centimeter, 2 centimeter, or 3 centimeters in diameter. And the target distances between the targets was either 6 centimeters, 12 centimeters, or 18 centimeters, giving us 6 indices of difficulty. Sorry, 9 indices of difficulty. There were 60 selections made at each of these indices for a total of 8,000 selections. So let's take a look at the results for error rate. This is a rather complicated table. First, on the left, we'll have the table top results. On the right, we'll have the table bottom results for each of the target distances, 6, 12, and 18 centimeters, and target sizes of 1, 2, and 3 centimeters. For tabletop input, we see for 2 and 3 centimeter targets, unsurprisingly, that the user is able to accurately put their hand onto the target. Those of you who are familiar with the test for drunkenness in the United States, when you're driving, will know that this is something that we're expected to be able to do well. With the 1 centimeter targets, however, we saw the problem of occlusion, where a user wasn't able to accurately select a target that was smaller than their fingerprint. And so we had rather large error rates for that size of selection. Now, when we look at the under-the-table selections, we see massive and huge error rates, which suggest to us that this is a silly idea and we should never have built a two-sided table in the first place. We see that for a 1 centimeter target, we have an error rate of 78%, so only 22% of the time is the user able to accurately select a target underneath the table. So we hang our heads in shame and leave? Well, no. Let's take a look now at how accurately they're able to make selections of these targets. We're not looking now at whether or not they landed on the target, but instead how far from the target they were when they landed. So this will tell us a little bit more about how well they understood the space underneath the table. And you recall, of course, that that was the goal of the experiment, not to see how accurately they could actually make selections. So for targets on top of the table, in centimeters, we have sub-millimeter accuracy on average. These are mean distances in centimeters from the edge of the target. For touches underneath the table, we see also that we have sub-centimeter accuracy. And interestingly, for the smaller targets, like the 1 centimeter target, the accuracy is generally within the diameter of the target that is the next size up. So what this suggests to us is that if you were going to try to make a selection technique that used under-the-table interaction, you should lie to the user about the size of the target, show a small target on top and have a larger input space target. What it also tells us is that the user does have a pretty good understanding of where their hand is. It's just not quite good enough to do these accurate selections. So our experimental conclusions are that the input is maintained, or the direct touch input paradigm is maintained, and that you shouldn't rely on the accuracy of land-on for your technique. So to summarize the talk, we presented a couple of different ways to do under-the-table interaction. The first was an inverted touch table, cheaper and easier to build than the other, and it has several interesting properties. The other was the two-sided table, which had even more interesting properties. I hope you'll agree. We demonstrated a few new affordances and fixes for tabletop input that this platform allows, and I hope you will agree that this is an interesting platform for future development. I would like to acknowledge all of the following people, especially Jacqueline Martino for her excellent diagrams in the paper, and Takeo Igarashi for sharing his source code of Smooth Teddy with us. And I'll take your questions. Anything? Tequila party stuff?
I have one question about the tequila party. So you mentioned briefly this idea of doing something off the table. Can you say more about remote user scenarios? Like what happens if you have two tablets at a distance? Have you looked at that?
Yeah, so one of the affordances I described of the two-sided table is that we can maintain the direct touch input paradigm when we're touching on top, but when we're touching underneath, send the input somewhere else. So for remote scenarios, you mean two users in the same location or users in different cities?
Yeah, different cities.
Um, it's an interesting thing to start to think about, and by having the second input surface so conveniently located, we can probably do switches between input here and sending input to a remote location. This might also afford having the ability to do some private input that you can only see in your location, and then when you're working on the bottom and then on the top, you can send the input to somewhere else. We haven't looked at that scenario in particular, but there certainly are a few things that that this might afford in an interesting way.
Other questions?
Come on, we bought your coffee. Let's see it.
Hi, Vincent Bell, Phillips Research. One of the things that I could see happening is that when you're interacting under the table, you're grabbing another person's hand. I was wondering if you had any comments on that from your participant.
Absolutely. So one of the issues with the inverted touch table, which of course extends to the two-sided touch table, is the notion of reduced reach. I said in my talk that this was because of the table blocking, but of course there are other social issues that might be implied. Being able to grab each other's hands under the table might afford interesting interactions that I haven't thought about. But it's certainly the case, even if you're comfortable that the user's hands aren't in the way, that if there are social issues with touch tables, and we believe there are, that you shouldn't reach very close to other users, the zone of comfort is probably even larger with touches that are underneath. So it's absolutely the case that if you're going to do two-sided multi-user input, you probably want to have the under the side interaction just directly in front of you and not with other users. Yeah, very good observation.
Hi there, I'm Stefan Rennick-Eggleston from the University of Nottingham. So I'm just wondering about the ergonomics of two-sided table use. So did you find it easy enough to find a comfortable height for users to interact on both sides of the table, or was that a difficult problem?
Very good question. So it was a challenge for us to find the right height. We wanted to make the table higher so that it would be easier to touch underneath, but then it got a little bit too high to be comfortable touching on top. In the paper, we described the ultimate height that we arrived at, but it did take a lot of work. So people who are going to follow this would be well advised to start there and look at the affordances of their particular device when deciding how high to put it.
Eddie Isaac from Columbia University. Did you notice if people wanted to put their dominant hand on top or on the bottom?
Another good question. So in our actual user study, we required the user to use their dominant hand. In the depiction that I have before, or even here where we show the dominant hand on top and the non-dominant hand underneath, that's for a lot of interactions probably how you're going to work, so that you have, as with the normal two-handed model for things, the non-dominant hand sets the kinesthetic reference frame for the dominant hand. But I would say it really depends on what type of input you're doing. So if you want really accurate input, you want to have the user put their dominant hand underneath. So it depends.
Okay, thank you very much.
Thanks.
Our next speaker is Sriram Subramanian.